Okay, this is our first in-lab class. I'm so excited. I hope you are too. We're going to be doing density this week, and we're going to look at it a couple different ways. The first way we're going to look at it is by making something fun, which is a density rainbow, and that'll teach you some techniques at the same time as allow you to have a really pretty outcome. A lot of people take pictures of it on their phones, and sometimes we even have a little competition to see whose density rainbow is the best. Anyway, so density, that's what we're doing this week. So what is density? Well, in class, we talked about the fact that density is equal to mass divided by volume. It's completely a measurement-based property. But what it really is, if you want to actually think about it at the particulate level, is it's a measurement of how compact the particles in a substance are, how close together they are. So, for instance, I have some particles, okay? Here are my, can you see this?
Yes.
Here are my 4 particles that are in my solution. We're going to really use our imaginations here. Right now, I have a certain mass and a certain volume. But now, you can come help me for this, I'm going to make the same particles, come on over here so they can see it, make the same particles take up a much different amount of space, a much larger volume. My density has decreased significantly. Less dense, come on in. More dense, okay? Thank you. Yeah. The cool thing about density is things that are less dense float on top of things that are more dense. And you're going to show yourself and prove that to yourself today. All right, so measurement of the compactness of the particles in a substance. It is an intensive physical property. Intensive physical property means it's not dependent on the amount of substance you have. And extensive, so it begins with EX, tensive, does depend on the amount of a physical property, on the amount of a substance that you have. So mass is an extensive property. Length is an extensive property. But density, boiling point, melting point, I listed a whole bunch of these in your lecture that are intensive properties. They are independent of the amount of material you have. Okay, so that's what we're going to be studying today. One of the things you need to know is, yes, the standard unit for mass is kilogram, but we're going to be using the gram because that's what our balance is mass in. We're going to be using volume of not meters cubed, that would be bad. We're using volume of centimeters cubed or milliliters. Now remember, these are interchangeable, but sometimes I have an awkward substance, like I'm coming forward, like this. Okay, can you see it if I put it right in front of you here?
Yeah. No,
No,
you can't
okay.
put it down.
This is called a slug. It's an old-fashioned weight you put on some sort of balance. I don't know, I haven't ever seen one of those. And this would be really, really challenging to find the volume of. Easy enough as far as measuring the cylindrical part, but there are dents and breaks and this little hook. So finding the volume of this by measuring to get centimeters cubed would be virtually impossible. So what we do is we get volume displacement, water displacement. That's how we're going to figure out our volume of this awkward substance. So first of all, this is just food coloring so that hopefully you can see where it starts. First of all, we'd fill up our graduated cylinder to a certain point. And in this case, I would look at you can't see it, but I can. The volume of this is 54.8, using my proper significant figures, two known for sure, 50, and then 4 lines up, but the meniscus is just shy of 55, so it's 54.8, and I'd write that down. Then, carefully, do not drop this in or you'll break the bottom out of the graduated cylinder. Been there, done that. Tip it on its side and slide. Watch it break anyway. Slide the slug down into the graduated cylinder. Now, I'm going to take a reading, and you can't see it, but I can. This is now 65.2 milliliters. Again, 65, and the meniscus is just above that, so 65.2 milliliters. So now the volume of the slug is the difference between the two, right? I didn't add any more water. I didn't lose any water. I slid it down in. The difference in the volume is due to the slug. That's how you find the volume of an awkward object like a rock by volume displacement. So most of our volumes in lab are in fact going to be done in milliliters. So in lecture we've been talking about densities as grams per centimeter cubed. In lab we're going to be dealing with densities that are grams per milliliter. Okay? So that pretty much covers the density part. Let's actually talk a tiny little bit about what we're actually doing. One of the things you're going to be doing today is using a burette. This is the second part of the lab. You're going to be using a burette. And this is my pretend burette. Of course, you're going to be able to see one. You've already seen one on your videos, and you'll be seeing one in lab. Burettes read going down. Okay, so the very tip top of the burette is 0.00 milliliters. And as it goes down, as you deliver the liquid out of the burette, don't put solids in a burette, as you deliver the liquids, you're going to be able to tell how much you've delivered. So this isn't how much it contains. A graduated cylinder is how much is in here. A burette, the reading you're going to make is how much it's emptied out, how much it's delivered. So you read going down. Now in this case, I've drawn my meniscus a little bit, probably more obviously than you'll be able to see it. But a meniscus, due to the surface tension of the water and the adhesion of the water for the glass surface, has a little bit of a dip. And you're going to read the volume right at the bottom of that dip. So if we look at my blown up burette, I've already gotten to 12 milliliters. And the next big mark is 13. So each one of these little marks is 0.1 milliliter. So as I read down, I have my solution down here below this meniscus. I have delivered 12, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. I have delivered 12.7. Now my next line was right here. So I have delivered 12.7, but it's not right on the 0.6 or the 0.7. So this is where you approximate. Remember, your significant figures in the lab are all the numbers you know for sure, and you know 12.7 for sure. It's at least 12.7, but it's very close to that. Now you make your approximation. So I would say that's, I don't know, 12.76. Aaron, what do you think it is?
I'd say 12.77.
12.77. What do you think it is?
I think 12.75.
And she thinks it's 12.75. notice that all three of us have a slightly different approximation, and that's fine. If Aaron had said that that was 12.70, that would have been wrong. If Mr. Proetta had said that was 12.80,
12.80.
that would have been wrong, okay? You have to be close. It has to be what we call reasonable. That approximation has to be a reasonable number, okay? So you're going to be using a lot of burettes today. Make sure you read them correctly. Once you have finished your second part, which if you've watched the video, which you better have watched the video that Mr. Proetta did of the second part of the lab, you're going to find that you have accumulated a number of masses and a number of volumes. And we're going to plot this with the mass on the x, the volume on the x-axis. Shoot me. I mean, what am I going to do here, right? And the mass on the y-axis. Mr. Sharlock's making fun of me, so it's all right to make fun of me. Mass over volume. So you're going to plot this, and I plotted some pretend points. And you can see with this that my points don't lie completely on this straight line, but they lie pretty well between the points. This is called a best fit straight line. And when you plot this on LoggerPro, that's what you're going to get, is a best fit straight line. And that best fit straight line will be given to you as y equals 1.109, for instance, x plus 0.0004621. Making it up as I get it, okay? I did a really good job here. When we take a look at this, remembering that this is our slope. Our slope is rise over run. Slope is rise over run. So I'm going to choose 2 points. And I'm going to get that out of the way so I can see the 2 points. I'm going to choose 2 points if I'm doing this without a computer that are not data points. 2 points on that line. I'm going to find the delta y, and I'm going to find the delta x. Rise over run. That'll give me the slope. So why did I not choose 2 data points? Well, check this out. Say I chose those 2 data points. That is a totally different slope than this is. You have to use the best fit line to find the slope. So what is the slope? Well, we have delta y. Our mass is going to be in grams. So grams. Our y, our volume, is going to be in milliliters. Milliliters. What's that? That's density. So in the second part, you're going to be figuring out the density of your unknown solution. You're going to be taking several measurements, and you're going to be plotting it on the graph and finding your density. Once you find your density, because it is an intensive property, not dependent on the amount, very much dependent on what the substance is. Very much, I should have said that to begin with. An intensive property is dependent on what? So is dependent on what the substance is, its physical state, and its 3D structure. In other words, that intensive property is going to tell me what, or be a good bit of evidence for what I've actually got. Your density of water is one thing. I change its phase, that's all I'm doing is changing its phase. I've got a totally different density for ice. Same thing for this. This is actually zinc. Zinc has a certain density when it's a solid. If I were to melt it, it would have a totally different density. Obviously, the density of zinc and the density of water are two totally different things. So you're going to be finding your density and then look at the list of unknowns that we have and choose the density that is closest to yours. Okay, so that's what we're going to do today. If you have any questions, make sure to ask your instructor or the TA that's in lab or Mr. Proetta. Be very careful, watch what you're doing, and we'll talk to you soon.